All right, on to 9.1. What this section is designed to do is to teach us about significance tests, just the basics of them. Remember, significance tests are also called hypothesis tests. Okay, so either nomenclature could be considered correct. So we'll read a couple sentences here, and I'll try to explain what they're saying. It says, the claim tested by a statistical test is called the null hypothesis, which we denote H with a sub O, and we pronounce that H naught. Null hypothesis will always have an equal sign. The hypothesis test is designed to assess the strength of the evidence against the null hypothesis, and this evidence comes from the sample. It comes from a sample. It says often the null hypothesis is a statement of no difference. The claim about the population we are trying to find evidence for is the alternative hypothesis, and we call that H sub A or HA. Alternative hypothesis will never have an equal sign. They will have a greater than, less than, or not equal to symbol. And sometimes the alternative hypothesis is sometimes called the researcher's hypothesis. Okay, so let me kind of explain what that means just in the context of an example. All right, so suppose someone tells you that the mean IQ score for adults in the United States is 100. So what they have basically told you is they have told you the HO, or the null hypothesis. Okay, so mu equals 100. All right. So the sampling distribution would have 100 right down the center. Okay, or the mu of x bar would equal 100 as well, because we know mu of x bar is going to be the same thing as mu. All right. So let's say we don't believe that. Okay. So we might believe it's greater than 100. Let's say we think that people are smarter, or we might think that people aren't that smart. So another alternative hypothesis might be that mu is less than 100. Or we could just believe, well, we don't believe it's 100. We just might believe it's different than 100. Okay, so that's how we would write our hypotheses. Okay, and we would write those hypotheses under step 1, which would be our statement. Okay, because we're making statements. Now, the only way, I'm not going to be able to get everyone in the United States to take an IQ test. They're probably too scared. Okay, so what we're going to do is we're going to take a sample. Okay, we're going to get an X bar. We're going to get a mean IQ score. All right, now depending on where that mean IQ score is, let's just say, for instance, that it's 98. Okay, let's say we take a sample and we get a mean IQ score of 98. Okay, that would fall somewhere to the left on the sampling distribution. Okay, now the question that you're going to really ask yourself is this so far away from this where you no longer believe that's true? Remember, we get natural sampling variability with every sample. Okay, just because one sample gave us a result of 98 doesn't necessarily mean that this average is not true. The question is, how far would this have to be away from this line where so you could believe that that's not true anymore? So you would disbelieve that. Okay. That's where this idea is. If we get an X bar that's so far away on either side of the mean, I no longer believe this is true anymore. So that's the whole purpose. Now, when we write hypotheses tests, okay, these things that go over here, these are always parameters. Okay, we're always making some generalization to the population. Okay, you'll never have an X bar right there or here. Okay, you'll never have a P hat in that spot either. They're always going to be mu's and rho's, and later we'll learn about this thing called beta as well. Okay, so they're always mu's, rho's, just population parameters. They always have to be parameters. And this is sometimes just called the mu naughts or the hypothesized value. So hopefully that clears that up a little bit. All right, let's keep going on the note card. Let's just look at an example. Okay, it says, does the job satisfaction of assembly line workers differ when their work is machine-paced rather than self-paced? One study chose 18 subjects at random from a company with over 200 workers who assembled electronic devices. Half of the workers were assigned at random to each of two groups. Okay. Both groups did similar assembly work, but one group was allowed to pace themselves while the other group used an assembly line that moved at a fixed pace. After 2 weeks, all the workers took a test of job satisfaction. Then they switched work setups and took the test again after 2 weeks. Okay, so this is a matched pairs design. Each person is acting as their own control. Okay. It says the response variable is the difference in satisfaction score, self-paced minus machine-paced. So they did the self-paced, they did the machine-paced in whatever order, it's random order, okay, or random assignment, okay. And then we're describing this difference as the self-paced score, okay. The score they gave, or the assessment score when it was self-paced, minus the assembly line score. Okay, their satisfaction when working on an assembly line process. Okay, so each person would have a difference. Okay, each person would have a difference. So it says describe the parameter meaning coming from a population, okay, in this setting. So when we examine each of the 18 persons' differences, we could take a mean of the difference, and that would be a sample mean. So I can call that X bar sub D, meaning the mean of the sample of the differences, of everybody's differences. Okay, so for example, if someone rated doing self-paced 100, and that same person rated assembly line score of 75, then that person would have a difference of 25. If you did that for all 18 people, we could then take the average of that difference, and that's what this would represent. Okay, so the parameter we're interested in is mu sub D. Okay, what does that represent? That's the true mean difference of all workers in this company okay, and satisfaction of self-paced work over machine or over assembly fixed pace work. So part B now says, state the appropriate hypotheses for performing the significance test. So there's going to be a null hypothesis and there's going to be an alternative hypothesis. Okay. So there's at the beginning how we write these, they would both be mu sub d's. Okay. Now it's asking me, is there a difference? So if there was no difference, if I subtract these from each other, I'm just going to get 0. Okay. And my null hypothesis is basically a statement of no difference. Okay. Now, what about if there is a difference? It's asking me, are they different? Is self-paced, do workers prefer self-paced over assembly line paced? Okay, either way, it doesn't say which one has to be higher. Okay, so the alternative hypothesis is there a difference? Is there enough evidence to suggest a difference? So these would be my hypotheses for this example. Notice these are parameters. They're both means. Now we already talked about this next section, okay, a little bit. It says the alternative hypothesis is one-sided if it states that a parameter is larger than the null hypothesis value, or if it states that the parameter is smaller than the null value. So these two things, okay, these two things right here, they would be considered a one-sided test. Okay, either larger or smaller. All right. And it says it is two-sided if it states that the parameter is different. A lot of times the words they'll use is, does it differ? Okay, like it did up in the previous example. All right. So if it's different, this is like a two-sided test. All right, now let's keep going. It says the probability computed assuming that the null hypothesis is true, that the statistic, such as a p-hat or x-bar, would take a value as extreme as or more extreme than the one actually observed is called the p-value, or the probability value of the test. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. Do not confuse a p-value with a sample proportion, which we call p-hat, or a population proportion parameter, which we would call rho. So let me try to explain what that means. Okay, so let's just look at a one-sided test. Okay, so let's go back to the IQ example. Okay, let's say that our null hypothesis is that someone tells us that the mean IQ score is 100. Okay, so 100 would go down the middle of our sampling distribution. Okay, but we actually think that it's greater than that. Let's say that we think it's greater than 100. All right, so we take a sample, okay, and we get an x-bar of, say we get something really high, like 115. Okay. Now, based on how many people we sample is going to determine the spread of this sampling distribution. Okay, but 115 is going to be somewhere out here. So what a p-value actually is, okay, that area there would be the p-value. Okay, so a p-value is the probability that we get a sample mean of 115 or greater, assuming that the null hypothesis is true. Okay, so if we assume that that's true, whatever the math on the normal curve gives us, or on our calculator, okay, whatever the math gives us, that gives me the probability that that actually happens, assuming that's true. So the smaller the probability, okay, the smaller this area, okay, the less likely that would happen, but this is what we observed. Okay, so the smaller the p-value, the less area the p-value, that's actually more evidence to start believing that this is no longer true. Okay, it gives us the ability to reject this hypothesis. Okay, There's kind of a saying in statistics, and it's not really politically correct, but we say when the p is low, we're talking about the p-value here, okay? When the p is low, we reject the hoe. Okay, so if it's not very likely to occur, but it does, we no longer think that's true. So that's the whole point of a p-value. And likewise, if it was a test the other way. So, in an instance, if it's, if our alternative hypothesis is that it's less than 100, and I get a sample mean of 80, okay, this probability would be really low. The probability that we would actually observe something 80 or less than 80, it's a really low chance that would happen, but it did happen, so I no longer believe that's true. Same concept. If it's a two-sided test, you would basically, if the alternative hypothesis says that it's not 100, and let's say it came out to be, I don't know, 90, well, 90 would be here, but since it's a two-sided test, we would have to add up all this area. We would also have to add up area on the other side, equally distant. Okay. Then we would have to consider this area. Okay. Well, that probability doesn't look quite as low anymore. So I would probably I wouldn't have enough evidence to say that that's not true. I would have to still believe that this is true. So the whole evidence piece comes from whatever your sample data reveals. The further away your X bar is away from the mean, the more evidence you have to say that that's no longer good. That's the whole point. And it could be for means, and it works exactly the same way with proportions. Okay. So for instance, if you believe that someone told you that in the presidential election, 50% of the people voted for Trump or Hillary, okay, and if you don't believe that, that's how you would write your hypotheses. It's all based on normal curves. Okay, so 0.5 is there. Maybe we took an exit poll, simple random sample, an exit poll, and maybe we got, in our sample, maybe we only got that 35% voted for Trump or for Hillary, whoever your candidate du jour is. Okay, so 0.35. If it was a two-sided test, all right, you'd have to do 0.35. You'd have to figure out what this area is, but essentially you'd have to double it because you have to look at the other side as well. So the other side would go from 65 up. You would take this area and you would examine how likely is it that we would get something less than 35 or more than 65, considering that this is true. All right, the smaller this area is, the more likely we are to believe that that's no longer true. That's the whole idea behind significance tests. Okay. So at the bottom of this page, it just kind of reinforces that first example. So we're going to continue on that example. It says data from the 18 workers gave a sample difference, we should really write that as X bar sub D, of 17 and a standard deviation of 60. That is, the workers in the small sample rated the job satisfaction in the self-paced environment on average 17 points higher. Okay. So we took everybody's difference, we added them all up, and we divided by the 18 workers, and on average, each person said 17 points higher on a satisfaction scale, whatever satisfaction scale they used. It says researchers performed a significance test using the sample data and obtained a p-value of 0.2302. It says, explain what it means for the null hypothesis to be true in this setting. So Our null hypothesis was that there was no difference, that the mean difference was 0. Okay, but we got an x bar of 17. Remember, this is a sampling distribution, so all these are x bars. Okay. So what the p-value represents is that area. Not just that area, okay, because you got to remember, this was a two-sided test, so it's not just this area, it would also be symmetrically that area as well. Okay. So these two pieces together add up to be 0.2302. Just to remind you, our null hypothesis was that there was no difference, and our alternative hypothesis is that there was a difference. Okay. So what does the p-value tell us? What does this thing tell us? It says, assuming that there is no difference in job satisfaction between the two types of work. Okay, assuming that there is no difference, our sample or we shouldn't say that. We should say there is a 23.02% chance of observing there's a 23.02 chance of observing a sample that had a difference of, since it's a two-sided test, it could be plus 17 or it could be minus 17, of greater than 17 points. Why do I say greater than 17 points? Because it's 17 or more on that side, or 17 or less on that side. So there's a 23% chance that we would observe a sample that extreme, that or more extreme. All right. And I just answered part B. That's actually the answer to part B. That's the meaning of the p-value. Okay. What does it actually mean for the null hypothesis to be true? For the null hypothesis to be true, means that there is no difference of job satisfaction. And that's what the null hypothesis says. There is no difference in satisfaction, that the difference is 0. That means there is no difference between the two types of work. All right. In part C, ask yourself, is that low enough for you to believe that it just doesn't happen by chance? To me, 23%, that's a little bit more than a 1 in 5 chance. Okay? That's not low enough for me to believe that there really is a difference in satisfaction. So eventually you're going to learn about this thing called alpha. Okay? Most of the time we set alpha to 0.05. If we would get a p-value that's less than 0.05, we can generally say, okay, that's not true anymore. All right, that a probability of 5% or 0.05 means that there's only a 1 in 20 chance that that would actually happen if the null hypothesis is true. That's a really low probability. So we usually set our alpha at 0.05. In some cases, some alphas are 0.01. You need a lot of evidence to reject the null hypothesis. Okay, so I would say something like this. Since the chances of getting a sample this extreme, okay, since the chances of getting a sample this extreme are still relatively plausible, I do not believe there is enough evidence against the null hypothesis in favor of the alternative. So in other words, this area, it's too big. Okay, it's too big for me to believe that that's not true. All right, I still believe that this is true. That would have to be much smaller. The area would have to be much, much smaller for me to get rid of this assumption, to get rid of this hypothesis. So we'll read the next part. It says, what is alpha? Alpha is called a significance level. It is similar to a confidence level when performing confidence intervals. For example, an alpha of 0.05 is similar to a confidence level of 95%. So those two kind of add up to 100. You can think of it the same way. Okay, the problems that you will encounter will give you the alpha or the significance level. If they do not, we must assume an alpha before we actually begin the hypothesis test. And you can do that based on prior research if it's available. If we do not have prior research, the most common significance level to choose is an alpha of 0.05. So after we actually perform the test, we compare the p-value, and remember the p-value comes from the area that's given by the sample, okay, given by the x-bar, okay. It says if the p-value is smaller than the alpha, our predetermined alpha, remember we predetermine alpha before we start, so that's why we say when the p is low, reject the host. So if the p-value is smaller than our alpha, we say that the data are statistically significant at that level alpha. In that case, we reject the null hypothesis and conclude that there is convincing evidence in favor of the alternative hypothesis. Again, we have it here again. When the p-value is low, reject the hope. All right. Now, for some reason, our area of our curve is bigger than alpha, then we never say that the null hypothesis is true. What we actually say is that we fail to reject the null. So like in a courtroom, think about a courtroom, you don't say innocent. In a courtroom, the presumption is not guilty. All right? And the alternative is guilty. So we need enough evidence, okay? We need enough evidence to reject that and to accept that, okay? We never say a person's innocent. We say a person's not guilty in a court of law. And there's got to be a preponderance of evidence, or there has to be, beyond a shadow of a doubt, of proof that the person is guilty. So we presume not guilty, we do not presume innocence. And there's three things you need to know, or three things you need for your answer when performing a hypothesis test. You always have to, this is to get full points on the AP exam. You always have to link your p-value. There has to be linkage between the p-value that you get from your calculations and the alpha that you predetermine, you have to say whether you reject or you fail to reject the null hypothesis. And you have to somehow state in context that evidence either supports or does not support the alternative hypothesis. All right, so let's read another example here. See if we can understand these alphas and p-values. It says a company has developed a new deluxe AAA battery that, not us, but is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Seems like a pretty fair thing to think about. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. Okay, the company selects a simple random sample of 15 of the new batteries and uses them continuously until they are completely drained. A significance test is performed using the hypotheses. Okay, we're going to assume that the new batteries have an average of 30 hours, and the alternative hypothesis is that we're trying to prove or show evidence that it's greater than 30 hours, where mu is the true mean lifetime of the new deluxe AAA batteries. And it says the resulting p-value is 0.0276. So if we were to think about this on a graph, we're going to assume the new batteries last for 30 hours. Okay. And the alternative is that they're more. Now, when we run our calculations, we find that this area is 0.0276. So this is where our x-bar was. They don't tell us what the x-bar was, but they tell us that the p-value is 0.0276. So what does that mean in context? Okay. If the new batteries really do last 30 hours, there's only a 2.76% chance that I would get a sample that lasts that long. Okay, there's only a 2.76% chance that I would get a sample as extreme as the one that we got. Okay, which is a fairly low chance. 2%, it's almost 3%, about 1 in 33, 1 in 40 times, somewhere in that range, that we would get a sample that extreme. Not that likely to happen. Okay, so it says, what conclusion would you make for the following significance levels? So if I predetermined my alpha was 0.05, well here the p-value is less than alpha. So when the p is low, well this is still low, but it's lower. Okay, so our decision would be to reject the null hypothesis. We would say something to the effect is, there is statistically significant evidence at the alpha equals 0.05 level to indicate that the new batteries last longer than 30 hours. So basically, when I reject the null, I'm accepting the alternative, but I never actually use the word accept. I'd put it back in context, but never actually say that you accept HA. Okay. Because in truth, we really don't know, unless we had all AAA batteries. We really don't know. Okay. We're just saying that there's evidence at that significance level to show that the new batteries do last longer than 30 hours. Now, in part B, it's a much lower alpha level. It's going to be much harder it's going to be much harder to get rid of HO. Okay? So in this case, our p-value of 2.76% is actually greater than the alpha. So in that case, we fail to reject HO. That's why we always choose the alpha before we run the test, so we're not fixing our results. Okay. There is, and then what we would write in our conclusion, there is insufficient evidence, okay, or there is insufficient statistical evidence at the alpha equals 0.01 level to show that the new batteries last longer than the old batteries, something like that. Okay, so my conclusion is kind of twofold. We either say there's statistically significant evidence or there's insufficient statistical evidence. And what that is based on our decision to reject or fail to reject. Okay, if it's reject, there is. If it's fail to reject, then there is insufficient. There is significant evidence, there's insufficient evidence. Okay. So that would be our conclusion. So when we actually go through the whole process of a significance test, we're going to use that same thing, SC-CDC. Statement, which involves the hypotheses themselves. You do have to do a condition check just like you did before. We're going to do calculations. We're going to make a decision and linkage. That's what this is, decision and linkage. And then we're going to come to a conclusion, which is circled here below. So that's the idea behind it. All right. So, now, this whole hypothesis test is a little bit harder than confidence intervals. Okay. So when we make a decision, okay, two things can happen. All right, if our mu is there, or if our rho is there, okay, we make a decision based on this p-value. Okay. Everything is based on this p-value and on the alpha that we picked before we started. Okay. The problem is we could be wrong. Okay. Maybe I got one sample that was just really extreme, was on the edges. Okay, this might still be true, and I just got a really high sample, for instance. Okay, so that could be it. Or in another case, maybe I got an X bar that was much closer to the mean. Okay, so that had a huge area. I could not reject this. I would fail to reject that, and that could actually be false. Okay, so you can make one of two types of errors. Okay, you can reject that when it's really true, or you can fail to reject this when it's really false. And that's what this explains, the type 1 and type 2 errors. Okay, so the type 1 error is if we reject it, if we get rid of this, okay, when it's actually true. It says the probability of committing a type 1 error is the same as the alpha level. And you pick that. You pick that where the problem tells you what it is before you start. So the probability of committing a type 1 error is always equal to alpha. Now, a type 2 error is not being able to get rid of this, not being able to reject this. If we fail to reject this null hypothesis when it really is false, our evidence wasn't good enough to get rid of it. Okay. when it's really false. Okay, so we don't know if it's false or not unless we were able to get everybody in the population. And so that would be a type 2 error if we fail to reject the null hypothesis when it's really false. And it says the probability of committing a type 2 error is called beta. Okay, and it says note we can only calculate beta by computing the power of a test first against a different alternative hypothesis. Okay, in your textbook, it tells you what the errors are. So let's just kind of think about what this table is saying. Okay, so if you reject the O, when you reject the null hypothesis, and let's assume that it really is false. Okay, so if you reject the HO when the HO really is false, you made a correct decision. Okay, if you fail to get rid of the null hypothesis, okay, if you fail to reject it when it really is true, that's a correct decision. All right. Now, if you get rid of, in this first diagram, all right, if I reject if I get a really extreme sample and I reject this, but it really is true, that's a type 1 error. And the probability that I make a type error, I determine that because it's set by alpha. Okay. Now, if I fail to get rid of this when it's really false, that's a type 2 error. And the probability that I commit that type of error is beta. Now the next part, kind of hard to understand. We will do an example. Actually, I'll show you how you can calculate power, but it's a little bit harder, how you can calculate beta and power. So it says the power of a test, okay, know this definition, is the ability of that test to correctly reject the null hypothesis, okay, in favor of a true alternative hypothesis. Okay, so the power of a test is the ability to correctly reject the null in favor of a true alternative. Okay, that's the main thing you got to know. The power is the ability to correctly reject the null. Okay, to make a correct decision, basically. All right, if HO, so you draw your graph. Okay, if your null hypothesis is at that value, the hypothesized value, you get a sample that's really extreme. Okay, so you reject this, but you do it correctly. You say, all right, that's no longer true when it's really not true. All right, I just have power. So that's what we're doing there. So how do you figure out what beta is? How do you make a type 2 error? Okay, the probability of making a type 2 error. All right, it's simply 1 minus beta. Okay, so if I rearrange this equation, beta would simply be 1 minus the power. If you rearrange this formula. So to figure out what beta is, you gotta do 1 minus power, but I gotta show you how to do power. Now there's a couple different ways that you can decrease your chances for error. So the only real way to decrease your type 1 error, okay, either make your alpha smaller, okay, or increase the sample size. What does increasing the sample size do? It condenses your sampling distribution. Okay, by choosing a larger sample size, you condense that. And by condensing it, you don't need quite as big of an X-bar. Okay. You don't need as big of an X-bar to reject the null. Or any X-bar you got, assuming it's close to the center, would have more area, which would make you less likely to reject. Okay. Ways to decrease type 2 error, increase alpha. So what's important to know is this Okay, the relationship between alpha, beta, and power. Okay, if you notice here, there's a direct relationship between alpha and power. As alpha goes up, power goes up. There's an inverse relationship to beta. Okay? If alpha goes down, power goes down, and beta goes up. So it's sacrificing one or the other. Now you might ask, what's worse, a type 1 error or a type 2 error? That depends on the context of the problem. Sometimes type 1 errors are very, very serious. Sometimes type 2 errors are serious. You should think about the context of the problem, because the way they usually ask these questions on the AP test, they'll say which kind of error, what would it mean to be a type 1 error in this context? Which one do you think is more serious and why? So you have to be able to logic your way through what would the errors be in that situation, and which one do you think is more serious? Okay. So again, alpha and power directly related, they go in the same direction. Beta is negatively correlated or inversely correlated to those other two. All right, so let's do some examples of this. So it says, example A, it says you read that a statistical test at significance level alpha equals 0.05 has a power of 0.78. What are the probabilities of a type 1 and type 2 errors for this test? Okay, so a type 1 error, the probability of making a type 1 error is going to be equal to alpha, which it tells us is 0.05. That's it for that. Okay. What's the probability of a type 2 error? That's going to be equal to beta. And the way I find beta is I say power equals 1 minus beta. It tells me that power is 0.78. Okay. Move the beta to that side, subtract the 0.78 on both sides, and you would get beta equals 1 minus 0.78. Okay. So beta is 0.22. So in context, there's a 5% chance of making a type 1 error. There's a 22% chance of making a type 2 error. Okay. So there's a 5% chance that I reject the null hypothesis when it's really true. There's a 22% chance that I fail to reject the null hypothesis when it's really false. So let's do part B. It says that you read that a statistical test at the alpha equals 0.01 level has probability 0.14 of making a type 2 error. So the probability of a type 2 error equals beta equals 0.14. There's a 14% chance of making a type 2 error. Okay, what's the power of the test? So they're asking me for power. So that'll be just 1 minus beta, or in this case 1 minus 0.14. That's 0.86. The power of the test is 0.86, which is a pretty strong power level. We'll go over this more in class, guys. We'll do examples. So let's try this. It says, let X denote the IQ of a randomly selected adult American. Assume, a bit unrealistically, that X is normally distributed with unknown mean mu and standard deviation of 16. It says, take a random sample of 16 students so that after setting the probability of committing a type 1 error at alpha equals 0.05, we can test the null hypothesis H naught mu equals 100 against the alternative hypothesis that the alternative is greater than 100. It says, what is the power of the hypothesis test if the true population mean were 108? So here's what this means. So I have some curve, some normal curve, sitting at 100. Okay. And we'll get more into this a little bit later. Okay. But the important thing to know is that we have an alpha level of 0.05. Okay. So this alpha is predetermined for us to be right there. All right. So let's think about some other alternative. They're giving me an alternative to the mean. They're saying 108. So right now, before we get to the 108, if I get a sample, if I get an X bar that gives me a p-value of 0.05, I would reject the null hypothesis. Okay. So this is like my cutoff point. Okay. That's my cutoff point. That sets the rejection region. So if I get any X bar to the right of that, I'm going to reject the null hypothesis. And make another normal curve here. And this is some alternative null hypothesis of 108. Right. So what I'm doing essentially is the power of this test. Remember what power means. Ability to correctly reject the null hypothesis against some other alternative. It's the ability to correctly reject some null hypothesis against some other alternative. So if I'm rejecting the 100, that means I'm over here in this rejection region. And if I take that rejection region up, okay, where it meets the blue curve, the power of the test is actually graphically all of that blue area. Okay, this right here would be the power of the test. And what beta would be that area right there. That's what the beta would be. And that's the probability of getting a type 2 error. So that's how alpha, beta, and power all kind of work together. And we'll do this in class. We'll go to this website and we'll do an actual example of calculating power. Now, on the AP test, you're not going to be required to calculate power. Calculate beta or power. You will have to know what power means, okay, which is this. And you'll have to know the relationship between alpha, beta, and power. You also have to know that power equals just 1 minus beta. So for instance, if alpha goes up, that means power will go up and beta will go down. And vice versa. If alpha goes down, power goes down, and that means beta goes up. Inverse relationships. You'll have to know certain ways how you can reduce type 1 and type 2 errors. But if you think about this graph, you can probably logic your way through it. Okay, so for instance, if your alpha goes down, if that number goes down, this rejection region gets slid further to the right, which means the blue curve also has less area, and the black curve would, or the black area would be bigger. So if alpha shrinks, we got a bigger black, we got less blue. and vice versa. If alpha is expanded, that red part gets moved further, less black part, more blue part. So that's what we're doing. We will do an example just so you can understand that better. All right. So that's enough about the theory. The next section, we're actually going to go through an example where we run a full hypothesis test. We're going to start with a proportion so you can understand that. And then we will move on to means in section 9.3. All right, so remember inference, all inference, confidence intervals, hypothesis tests. You got to know how to do both of them. I'll wrap that one up right there.